Yeah. And you need to turn on the mic, like, yeah, the thing on. Yeah, I believe you can share the screen on the Google Meet as well.
Share the screen on the Google Meet.
No, that one, bottom middle. And let's see. Do you need a pointer, or should be okay?
I don't have pointer, but at the moment I don't think I need one. Is this one?
This is a pointer.
Okay. Google Meet, maybe I need to log out and in again because it opens in Safari and
Okay.
it's a little bit slow. Okay.
And you had the GitLab. I thought I shared the GitLab. Hang on. Guess I didn't. Give me a second. I'll join. I will input.
Hi.
Okay. All right. So, are you sharing? Yeah, I can see that you're sharing that one, and we should be good to go.
Okay.
And so today we have Wooyoung, who is a postdoc in our lab, and she's been working on white matter analysis pipeline. So, kind of a couple of weeks ago, we had the functional connectivity and the geodesic distance by Yan Cheng. And then following that, we had from those functional connectivity types of indices, we talked about the transitions, functional transitions. So it's like an advanced derivative from the functional resting state data. Instead of just looking for connectivity, we look for functional state transitions and that was Junwei's session last week, or last week, yeah. And then so now today we have Wooyoung, who will be talking about when we have functional connectivity between two regions, and when they have a geodesics kind of relationship or modulation, like from when Yan Cheng showed us, as distance goes, the connectivity drops. But we have white matter paths and tracks in the brain as well. So how does this all get integrated into one huge connectome? It's not just a functional connectome, it's not just a structural connectome, it's some sort of integration of both. And so today, Wooyoung will be showing us her pipeline. Right, thanks.
Okay. So before I start, I want to share the basic core question where our analysis started. So like for the Yan Cheng's gray matter analysis, we are trying to find the shortest distance between the voxels, right? So if you just pick up one voxel in the gray matter, and then we can track the root of that voxel, goes from one voxel to the rest of the brain. But in the brain, we have gray matter and the white matter, right? So for like neural signal, if there's a one neural signal starting, just assuming that starting from the one voxel in the gray matter, it will start from the gray matter, going through the white matter, and then again going into the other part of the gray matter and then finishing in the gray matter. So given this route, we try to track down as a simple, what can I say, like the signal route from the one voxel to the rest of the brain. So for my analysis, it will be mainly about the white matter and then the signal from the gray matter going through the white matter part, from the white matter to the gray matter, the boundary. So the track signal route from the gray matter through white matter to the other side of gray matter. For the gray matter route, we are using the Yan-Chung's analysis for the geodesic distance on the cortical surface. And for the white matter, it's known as with the tracks. And then at the beginning, we try to find like every single voxel in the white matter, but technically it's impossible to calculate all the voxels in the white matter. So at the end, we're just, okay, just make it feasible. So we're decided to work on the already predefined white matter tracks, but as many as tracks will be better, obviously. So we chose the free surface 42 tracks for this analysis. And the important part is that because the signal from the voxel from the gray matter going into the white matter, that part, and then from white matter to the gray matter, that part again. So I made the diagram here. So it will be the boundary between the gray matter and the white matter. It will be the critical part on this analysis.
I really like this graphic. I think this is good. Yeah.
So everyone okay with this concept and our questions? Then our key design principles is that it has to be under subject space, not going through the normalization or any further group analysis, because it's useful, but we're anyway losing some individual data, and then it might have some critical information about this person. So our principle is that we must keep everything in subject space. So how we made this possible is because anyway we have like a group template. We will run this pipeline over the subjects, but under the same group. So we are making the subject-specific template, and it's made up of every single participant of this group. But it's a representative for this group, not just like any other standard template. And then we will be using inverse warp to this SST, like already non-standard template into the subject-specific template. So templates comes to the subject, not the other way around. So for most of the group analysis data, we are using every single subject and then making normalization and then grouping and then making a one group template, and then we just run under this group template. But we first make the group template and then we inverse warp to the subject space again. So if you see on the right side, there are two different subjects of this group. But you will see they are different sides of the brain, different shapes of the brain, but they are still inverse warped with the AAL. So all the regions of the gray matter and all the things we want to know about this person goes to this individual brain. So we will not change any brain size or shapes.
Was this one done using FreeSurfer or?
Yeah.
FreeSurfer did this one.
Mm-hmm.
Oh, okay. Yeah.
And then another key design principle is that we will use voxel-wise resolution. But just as I just explained, that white matter is a little technical problem. So for the white matter, we decide to use the predefined tracks, but for the gray matter and other boundary and functional connectivity or the other part, everything kept in the voxel size level. So if you see this diagram again on the right side, I will explain more about this later again, but just briefly explain you about this diagram is for the one subject's brain. And then this gray part is obviously gray matter. And then when we are done with the analysis, we can just project these images like this mask over the brain, and then we can see like for the red part is one white matter track, which is corpus callosum genu. And then following this our analysis pipeline, we can see the green overlapped voxels, which is the overlapped region between the gray matter and the white matter. So basically this analysis pipeline consists of two parts, which is the gray matter and functional connectivity. That is already done with the Yancheng, so I'm not going to explain about this part. And for the gray matter, white matter pipeline that I'm going to show you this about today is about based on the DTI data and then using the tracular and the AAR telocyte propagation on the native space and then using other DTR scholars. So where the full workflow will be like this. Before we start the analysis, we first make the template. The template is about, like just I explained, is about making the SST, and then from the SST inverse warp to every single subject. And then we are going to use AAL that has to be also come together with the DSI and NTU, the white matter mask again, and then going inverse warp again to the subject space. And then basic pre-processing, including recon or tracular, that is already pretty random function. So this has to be run before all the processes. It will take like 2 or 3 hours altogether, recon or tracular. And then of course for the gray method, we have to do the segmentation and all those things. So this part is very important, but very, very basic and also taking a long time. And then the rest of the part will be mainly done by the Python script and then Bash script. So for the software, you will need the FreeSurfer over 7.2 version, because previous older versions, you only have the 18 tracks. So you cannot use the older version.
Oh, so this was it 42 tracks only came with this version?
Yeah.
And you cannot, they cannot like back up?
No.
Wow,
No.
okay.
So they changed a lot, like at the time when they updated like this version 7, they decide to upgrade a lot.
What's
so
the current version?
current is already 8.1 or something.
Okay.
So,
And that's the one we have, we are
Yeah.
using?
Yeah.
It's just that you're saying that you need at least 7.2.
Yeah.
Okay.
Yeah.
All right.
If it's less than 7, version 7, then you will only provide you only 18 tracks,
All
the
right.
old versions.
Okay.
So I briefly explain, or one step. Do you prefer like explain one slide and then show you the data, or you want to explain all and then show the data?
I don't know. Whatever works for you, I think.
Okay.
Whatever you think is easier for you.
Maybe one by one. Okay.
Sure. Okay.
So for the raw subject data, we would need to have the DTI, obviously BBAC, VVAR, and then of course we would need the T1 and the rest. But I will not explain much about the T1 and the rest. We just assume that it's already done with the Yancheng's analysis, and then we already have all the necessary data.
I can maybe give a little bit more, is especially for the rest part, right? Is that Yancheng's script or Yancheng's pipeline isn't just directly just the rest, because you have to apply the mask of the gray matter, right? And then you have to take out the voxels that are like where the signal is 0, basically. So because those are going to mess up the calculations. So Yancheng's rest has been pre-processed to do the denoising, motion correction, slice timing, and masked, and then extract the residuals, right? That's the denoising part, and then applying the frequency band pass filtering, and then finally also removing voxels where there's basically no signal to reduce basically the data to just only those essential gray matter voxels that have both signal fluctuations. So that's the rest that comes into this part. And I suppose the rest of those T1 DTI BVAC are directly from DCM to NIFTY. You just convert from the DICOM and you get all of these. And the only other thing is they must be co-registered to the rest. So the rest and the DTI and all that must all be in registration. Otherwise, obviously, it will fail also. Yeah, so those are the key things.
For the template preparation, I will not try using the data here, but I will just briefly explain because it's quite simple. We just open the DSI Studio. And then you have to first down the NTU DSI 122 data. This is simply based on the NTU DSI data. They've made a template using the NTU data. So good thing about this mask is that it's based on the Asian population, so it's quite similar to our brain rather than just using the Western data. And then because it provides the Y matter template, so we will open this NTU DSI 122 on the DSI Studio, and then it will just pop up because it's quite simple GUI like a con. So if you open DSI Studio and then load the NTU DSI 122, you can be simply downloaded it on the internet because they provide it for free. And then you just click the reconstruct and it will pop up and they will just pop it up and everything's ready. And at that point, you just load the ROI MNI voxel version 7 in 1 millimeter voxel as a region. Then they will just automatically pop in together and then realigned. And then you can save it and then using...
So is that step number 1, it's taking the NTU tracts templates, which are the diffusion values of the in the template, and then using the AAL ROIs to reconstruct those tracks, the main tracks?
Here the reconstruct means in the DSI Studio is actually when they load the mask and the reconstruct, they just load all the information on...
Oh, it's just loading. There's no computation involved. Okay.
Yeah, and then if you load the ROI MNI again, they will automatically match because it's already a standard template there, or the resolution, everything is they are matched. So you just can, like an overlay, you just load it overlay, and then you can save it together because then you will have this ROI information on this mask.
Okay. And then all these will be exported as a NIFTY file, which is that ROI MNI V7. What's V7? Version 7?
Yeah, version 7.
Oh, okay.
And then if you open the SPM again, and then using the SST, then you can inverse the information, you can load it, and then you can inverse warp. Then you will have all the information for the Y matter, which is provided by NTU DSI 122, and then gray matter region information by ROI MNI, and then or our subject template SST together. And then for each participant, you have to inverse warp again to the subject space. Then the one subject will have all the information for the Y matter, gray matter, and then group subject template. And then like I said, for the gray matter and the Y matter, before we start, we need to run the recon orb. The reason why we do the recon orb because to run the trochanter, you need to have the output from the recon. So anyway, you have to reconner first, which takes the longest time on this analysis.
I think about, what, 4 to 6 hours?
Not up to 4 to 6 hours as I calculated.
Less.
If you run on the server, like 3 to 4.
Oh, that's all right. Not too bad. Okay.
Yeah, for the command, it's just reconner and the subject, and then I tried to run the segment salami nuclei together in the reconner, but it didn't work quite well. So make it simple and clear. You first run the reconner, and then when it's done, you just run again the segment salami nuclei.
What does that do?
It will provide a little bit more detailed segmentation on the salami nuclei, that part. But it will be necessary after we run the trochanter, it will ask.
So trochanter needs it?
Yeah.
Okay.
So I include this all together as a script for my analysis. If you just pop it, okay, let me show you. Hold on. Maybe window. For the template, you see here, I just quickly mention that just before the DSI student and everything, I made a more detailed explanation here. It's already provided on the README inside here. And just for the Y method, reconner, if we open this one, we just can simply put the root directory setting here and the subject ID. Then we can run the reconner and then run the segment salami nuclei. And then if we meet any errors, then it will pop up showing the error. Yeah. So before we start, we already have the order directory setting. We basically have the raw data for the T1 and DTI. Then this is the script I used from moving the source data to the root and then making the necessary trees for the necessary folders. This part, GM parts are already done with the N chunks, it's the same. But like I thought that like there are too many subdirectory like in between the folders like session 1 and all those brain things, and I just removed it. So there will be the gray matter and the anatomical and the functional, and then there will be segmentation, QC processing, all those things, and they will be directly making the Y matter directory, which is I will show you. So for these subjects, let me say subject just one, there will be like 2 big directory, which is gray matter and the Y matter, and then we are going to talk about the Y matter this part today. And then if we run just basic, just bash script here, it will make the directory called the derived. Derived, there will be some output in the middle. And the free server obviously need this kind of format, because the free server requires this kind of format to run the reconner and then trochanter everything automatically. And then the reader, the final reader will be under this folder. And the trochanter folder actually, I will explain later what this is for. So for the raw data, we first need to make the directory setting and then run the reconner. When it's all done, then we need to run the track, or which is a trochanter. PPT again.
So that line at the bottom there is actually 2 lines,
Yeah.
right?
Mm-hmm.
So you have to run the recon all first. Then after that, when it's complete, then you can run the segment thalamic nuclei.
Yeah.
Okay.
So if you just want to run the single subject, you can just type recon or -s subject name and then -i subject data, and then just run or, and then when it's done, you can just type again segment thalamic nuclei and the subject. For the troculi, it's similar to recon or, it will be automatically.
Need to close that window. There's a.
Let me, or just let me share, not the screen, window.
Yeah.
This one, like
Yeah,
this.
yeah.
It's
Yeah.
better. Or
Yes,
do I have
it's
to,
okay.
Do I have to close it? Good.
Yeah, this
Yeah.
is fine.
It's working, right?
Yep.
I'm not off. Yeah. For the trocular, it will be run automatically, but you need to have to write a kind of like a preset. Like you need to have to provide like a form of your optional selection or whatever you want to run. You need to write in a text file. Then if you just put that text file in, then it will read this file and then run for the subject data. So trocula has a 3 part, which is the pre-processing and the bad folks, and then pass the track. So you will have to write something like this. This is called DMRIRC. So if you see on the right side, this is the bash script I made. So you have to first prepare your like configuring setting. Then you have to run like track or preparation, track or bad post X, and then track or pass track. It will have 3 steps. And then, as you know, we have a lot of data, and then you cannot just keep an eye on every single command line. So I made it into the script, and then let me show you. Okay. This is, so I made it into number 2. Subject, blah, 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 DMRRC. This is written based on our current data analysis group, NCKU. So you will have to write your subject directory and then set the root and then or the similar, and this is the basic, the original DMRIRC example provided by the trocula philosopher. So based on all these options, we need to set up specific data information about our subject. So you have to put your DTI path and then subject information.
The subject list is it repeat right now?
Yeah, because we have the NCKU data provide the DTI and a DTI reverse file, DICOM.
A DTI and a DTI
The reverse.
Reverse? What does that mean?
They have the source data, DICOM.
Yeah.
Have 2 folders.
Why?
They're scanning the DTI on the one side and the other side reverse.
Oh, the sequence has 2.
Yeah.
So they scan twice. We only scan one, right?
But NCKU, when they provide, they have 2 folders, and when I check, they say 1 folder is reverse.
Are they different, or are they
they're different numbers and
do they get combined? No. Okay, this is specific to the site, not a generic thing.
For the trocula, if you only have one sequence, one
usually it's just
sequence,
one, right?
then you just can write. But since we have 2, I just use them to both.
Sure.
Yeah.
Okay.
And then the reason why I wrote the twice is just technically you have to write twice, so it will read twice on this script.
But it's the same name.
Yeah.
So how would it know which one?
This DMRIRC file must be written per subject.
Uh-huh.
Yeah.
Okay.
So every single person has need to be one DMRIRC specific configuration file.
Okay.
Yeah.
All right. Oh, I see. Because so you see, number 2 is subject XXXX.
Yeah.
So this, if it's subject 1001, we'll have this one,
Yeah.
and then 1002 will have another one.
But basically, if you're under, if they are under the same institution and the same study, they're
You just
like all the
copy.
detail will be the same. Only the directory and the subject number, subject name.
Well, I guess you can do this way. Every subject has one of this. I mean, I would do it like, I would set this script up as a script, right? And then like at first I just say what subject, and then it will generate this script each time.
Yeah, that's why I did.
Yeah.
But the thing is that you have to, because I did some trial and error.
Yeah.
But when I did when we do the NTU SEC that data, it's quite simple because we have the Nifty data and we just can read the Nifty. But the thing is that when I did for the NCKU data, it showed up a little bit of error and it didn't work. So and then the solution I found is they just use a DICOM, not using the Nifty file.
Okay.
It's quite more accurate and then more faster in a way. So I didn't share on in here because it's not necessary for all the data. But for my case, when I did this subject, I made a script to read the first data of the DICOM folder and automatically put
generate
in,
this.
generate DMRI
Okay,
data.
so that would be the best way.
So it will be showing that this one will be like under detail folder. This is the first data of the DICOM.
Okay.
And then this is the reverse folder, and this is the first data name of that DICOM folder.
Okay.
So I made a script to read all these, look all the subjects, and then put the data necessary to this script.
Got it. I think, I think one motivation for doing what they did probably is that you acquire the diffusion in one direction, and then you acquire the diffusion in the other direction. And technically, if it's the same subject, then you can average it and it's more accurate, something like that.
Finding out the noise better and then make it more accurate.
Okay, but then it requires more time. You need to scan more.
But the reverse data, when I checked it didn't have as much as have the DTI sequence.
Really?
Yeah, similar in numbers.
Maybe it was a reduced version to save time, maybe. I don't know. Okay. All right.
Anyway, like if you need any kind of like specific script to make this faster, then I'm happy to help because I have some experiences in input, like for investing a lot of time to develop this. So anyway, for this case, you have to write the directory and the root and the subject list twice, and the first data name of the DTI and the DTI reverse. And then once you are making this file, it will be saved under, like for subject 1, Y matter, it will be saved under tracular. It will be the same as the one. It's the previous version. Because I updated it a few times. And then
I just realized that the Google share is not what you are sharing there.
Really?
Yeah, the Google Meet has a different share, which is fine. It's not critical, but you might want to switch the Google Meet share to
Google Meet. I'm sharing what? Show my.
And then
Window.
Yeah. Yes, now it's okay.
Yeah.
All right.
Okay, show you again to Google Meet. The code. For the convenience of use, I write the steps. So for first, making setting directory and then recon arm, and they are done with that, we are going to do track org. But for the number 3, before we have to write the DMIRC, which is number 2. Then if I show you Google Meet, can you see?
Nope.
No. So maybe I should share the entire screen, right?
Probably.
Right.
Yes. Okay.
So actually, the number 2, we are not running this script. This is for the number 3 command. We need to first prepare the number 2. But for the single subject, you can write, you can type by yourself. But like if you run the multiple subjects, then you can consider writing a script to automatically produce this file per subject. Then once the MRIRC is ready, then we're good to go with the number 3 track or loop.
So you put it into that DMRIC line there. Is that right?
DMRIRC line.
What the one that you just wrote for every subject, and it is called here.
For the convenience of use, I decide to write the subject.
Yeah, number 2 subject whatever. So
and the
here.
DMRIRC, but it doesn't have like dot something, so it's not a running script.
So is that config file there, that line? Okay.
So number 3, it will be the script, bash script. And then I have included this to avoid errors, because if you don't type this, it will always pop up the error that the environmental setting didn't go successfully or anything. So I decided to put in here. And then you have to write the subject numbers, and then your base directory, and then run, track org, preparation, and this is configuration file. You need to call the configuration file, which is number 2, DMIRC, and then once it's done, then we automatically go to the next step, which is about post-X. And when it's done, the number 3, the path tractography will be done automatically. Everything's done.
Bitpost is FSLs, isn't it?
Yeah.
So Tracula actually uses FSL.
Yeah.
Okay.
But it needs recon or output.
Sure.
Yeah. So they are all together. So once you run this, then you will see a free surfer, subject 1. So if you run the recon or, then you will see like this label, MRI, script, stat, surfaces, touch, and trash. And then once you run the Tracula, you will see like the prefix D folders, like D path, the MRI, the label. So if you see undergone to the D path, you will see like 42 folders, like, or the tracks. Right here, then under each track, you will see the endpoint, images, surfaces, and the path map, or the path and track related information, like for each track. So once you run the reconor and then track, or you have to go into the every subjects further, the path whether they have or 42 folders. Like this. Okay. And then Where's my Google Meet? Oh, mm.
Yep.
I will skip this first. It's a template. And the next will be the endpoint extraction. Once you're done with the recon or an intraocular, just like I explained, you will see the all the deep paths and everything track information already saved. And then each track has two endpoints, right? Just at the a diagram I show you at the first. You will see the Y meter in the between, and then you will see for example, endpoint will be here, and then another endpoint will be on another side, right?
Is it one voxel each? One endpoint is one voxel.
I will explain it.
Yeah.
For example, this script will find one voxel for each endpoint.
Wow.
Actually, there is not just one endpoint because track will be a bundle.
Yeah.
And then you cannot specify one voxel, right?
Yeah.
So it'd be bundle of a thread going from one side to the other side.
Uh-huh.
So there will be many voxels.
Okay.
Technically.
Yeah.
So if you open just now that deep path further, you will see the endpoint in this image. If you open this image, you will see
a bundle.
many voxels.
Okay.
You see all these voxels from here, this
Yeah.
side.
Yeah.
There are 5 voxels, right?
Yeah.
Like this, if you open that image, lift image, you will see this or that.
Okay.
Or
five,
this.
five,
Yeah.
five
So
dots.
Yeah. You will see the side of the endpoint.
Huh.
Side of the track. Just
Okay.
imagine it.
Okay.
So this script, this time, we will extract one voxel, one representative
Out of
voxel.
the, let's say 5,
Yeah.
you find one.
Mm-hmm.
Okay.
Then how do you decide that voxel is based on the density, weighted mean position. So for example, just right side on this image, just like I said, 1, 2, 3, 4, 5, 6, 7, 5, 3. There, but it's 0. 0 is not included as endpoint.
Anything
2, 5,
that's non-zero.
anything that is non-zero will be the endpoint of one track.
Okay.
The side of the track at the end of the track.
Okay.
And then there will be density because tracular calculation is based on the probability.
Yes.
Yeah.
Sure. So this will be the highest probability density.
Yeah.
Is the voxel that you pick. Okay.
Yeah.
Okay.
So there will be 2 representative coordinates.
That's reasonable.
Yeah.
So it's based on probability of connectivity from the diffusion data, and you are picking the voxel that represents this tract based on the maximum density, probability density.
Yeah.
Yeah. Okay.
And then because track is a bundle of voxels, there will be 2 endpoints.
Yes.
So there will be two representative coordinates.
Got it. Okay. All right.
And then over again, share continuous entire screen. So in this case, is to run the endpoint.
So which means we have 84
Yeah, 84 points
per subject.
Yeah.
Okay.
Because there are 42 tracks and then each track has 2 endpoints. Yeah, so if you run this script, you will see, wait, hang on. And I made all the script designated going to the derived endpoint, endpoint 1, for randomly picking up one track, then you will see there will be one coordinate, representative coordinate.
And this is in subject space.
Yeah.
Okay.
Yeah, like this.
All right.
So endpoint 1 will be one side and the point 2 is the other side. Dip, dip. And then how do you want to track the presentation? It's simple. Again, the data is saved under deep path, under like for example, and then picking up one. I think I can open, right? Do I have set it up here? I don't know. Oh, I think I have. Why? I don't know why. No. Okay.
You don't have it on your laptop?
Or no. Or can I try opening up
On the you mean server? Yeah, sure.
But from yesterday, I have some difficulty logging into Guacamole to the 50.
Oh.
I don't know why.
Which one is this?
50, or I have different data. I can try. But I don't know why. Sorry, because I typed the wrong password.
Oh, okay.
This is different subject,
Sure.
but let me show you. Because the pipeline is the same. It's okay. This one also. And the point. The path. It's not installed on 50. Or should I export subject? Right, so I have to do it. 56. Yeah, but I ran it before on 54, but because we are like updating servers and then changing things, right? So it's moved to the 50.
I think it's just that your FSL and free server paths are not set on this new environment yet. Yeah. So for now.
Yeah, for now.
Yeah,
never mind, but
yeah.
If you open like the endpoint Nifty files, then you will see like bundle of voxels just like skr. And then among those voxels, there's one representative voxel. And then how do you find? You just click it over around, or you just can write the coordinate based on our data. Mostly in the middle. And then yeah. And the next steps will be finding the matched endpoint between the gray matter and the white matter track. Like just now we did the tracular, and then we extracted the voxels and then all the images per track. Then we have the gray matter data. So we are trying to find like per subject where they match, like the boundary voxels, like where the gray matter mask overlapped with the each track. and then we are trying to find those coordinates of the voxels.
So for one tract, you have two XYZ coordinates. Then let's pick one of those. You find around there where is the closest gray matter voxel. And then
Matched or closest?
match or closest.
Yeah, one voxel away side in a.
The furthest radius is one voxel away. So anything that is two voxels away.
No,
No,
not
okay.
counted.
All right.
Because when I calculate like only matched endpoint, only matched the coordinate, because the threshold is too high, many will be gone. So we couldn't find the like really meaningful information because the coordinate has x, y, z. So each voxel, if it's one voxel away, two voxels away, is too big. So it's meaningless. So it's x for the x, even like for the x is counted as matched, but y, z not matched, but still counted as matched like that. Yeah. So this will be number 6, match endpoint. And then number 7 will be the matched coordinate into the binary nifty mouse image. So when I first tried to find like matched coordinate, and then this founded coordinate converted into image, save it as image again. It's number 7. Yeah, up to here, okay.
Oh, okay. So number 6 is just finding just
The coordinate.
But then number 7 is the coordinate, but then as an image.
Yeah.
Okay.
I divided it to make it simpler, and then I don't see. I cannot see. Okay. So let me see the code. Or do I can try? Sorry. Because I barely use this laptop to run the analysis. So if we open the number 6 matched coordinate, first we put the subjects again here, and then project root base, and then first we have to make the path setting, and then we have to core the C1 data, because C1 obviously for this subject is gray matter. And then when we core the C1 data, then it will automatically find between the endpoint 1, PD, this is the output of the tracular, endpoint, another endpoint, is saved as a nifty file, so it will find the non-zero voxel coordinate of this image, and then the C1 image with the matching plus minus 1 voxel away search.
Okay, this is number 6. Okay.
Number 6, step 6. And then it will be saved on output directory of match CSV. Will be saved under, like for the Python, this script, it will be run really quick. Match C1. So again, you will see a lot.
So each row is...
Okay, first column track name is the same. And the endpoint is whether it's endpoint 1 or endpoint 2.
Uh-huh.
You get it? This endpoint 2,
One.
and then you'll see the endpoint 1 at the bottom.
Oh, I
Oh,
see.
no, it's this is endpoint 2 only.
Oh, only
Then
endpoint
you will
2,
see the
okay.
endpoint 1 here in a different file.
Ah, I see.
Mm.
But this is one track, right?
For this track, the endpoint 1, and for this person's C1 mask, gray matter.
Yeah.
Mm.
But has many endpoints.
Endpoint?
So there's like,
Yeah,
so many rows.
Yeah, yeah.
So which means this person's splenium, endpoint 1 touches the gray matter at all these coordinates.
Yeah.
Okay. Okay.
Either X or either Y, either Z or either both, then you can see here. I match.
Yes.
IJ, this is 0, 0, 0, but tolerance past Y.
Yeah.
Because none of the IJ nor K matched, but they are under one voxel away. Tolerance, so it's passed.
Okay.
So if you see over here, then the jet, they are matched in the
one exact match.
Yeah, one exact
Okay.
match. Mostly like this.
Okay.
So you cannot say they are really matched a lot,
Sure,
they are not overlapped
sure.
a lot.
I mean,
And actually each track has different size.
Yep.
Yeah, so
Yep.
maybe this, or maybe you can see like maybe another, this one is a big track. Then you see a lot.
SLF. Yep.
Yeah.
Yep.
Or like this one.
So each track can have many, what do we call each row? Each row would be called a streamline or a fiber. What would be the correct term to say? Each one here is one track.
One voxel coordinate.
No. Like the whole file this is FAT, right? Which is the what? As
one track, yeah.
arcuate fasciculus, is that right?
Uh-huh.
So this is one track.
Yeah.
Then in each track we have many rows, right? So each row is based on one streamline of the track.
Voxel coordinate.
Each row is one voxel coordinate, but the voxel coordinate is every endpoint, because you said there are let's say 5 endpoints of the track. So each voxel is
one of the
5
yeah
densest.
Yeah.
So that's what I'm asking is what should we call that?
Yeah.
Is it streamline or
endpoint? One of the endpoint voxel?
Yeah, but it comes from average or of 5, right, or more endpoints coordinate, right? You just find the most densest.
Maybe
What is? Yeah,
maybe
I just want to get
answer you the question using. Where did it go? Come on. I want to open. Where is it?
Which one?
Google Meet. Maybe
Oh,
I drag
you
it
have to
down
click on Google Chrome or.
Here, I got it because
It jumped out. Yeah.
You see, like at the beginning,
Yes.
we had this diagram, right?
Yes.
So
Yes.
this is a 3D image, but like if you see on the 2D image over here,
Yeah.
maybe here.
Yeah. One
that the
green dot.
Yeah, one green dot is overlap the voxel.
Right.
So actually a lot, right?
Yeah.
The red, this is the whole track.
Right.
And then you can say like all these are endpoint at
Right.
the boundary,
Right.
at the edges of the track.
Right.
But based on the shape of the track, the number of the endpoint voxels will differ. If with the track shape like this, really huge, and then
Yeah.
if we spread over the area, then
Yeah.
the endpoint number
Will be more.
and then shape of the edges of the track, end
Yeah.
of the tracks will be really broad.
I guess each green dot comes from like the densest probability,
Also, yeah.
right? From many other smaller dots or many other dots. Is that correct? Is my understanding correct?
I'm not sure whether I understand you correct.
Because you said you showed that one where you had many densities, and then you pick the one that has the highest density.
That we are not using that one.
Oh,
we
then
leave
which
it,
one?
We leave it as just a representative coordinate. But the next step is not using that coordinate.
Okay. Just still using all those.
Yes, kind of different.
Okay.
Like for all of these endpoint voxels,
Yes.
the first step is to find the representative one voxel coordinate. Okay, leave it there.
So it'll be the average, say, sort of the average of all these green dots is the representative.
No. So the reason I put this step before this is because we are only using the endpoint coordinates.
Yes. These are where they have overlap.
Yeah, with the gray.
Where the endpoints overlap. But the other one is you have a lot of endpoints in the densest one, which may not be overlap, which
it's nothing to do with the gray matter.
Okay, got it. Okay, then no, okay, all right.
Okay,
I think that okay.
Just wrap it up again. The number 6 step to find the endpoint representative is among those only the Y method track. And then for this Y method track, there will be two bilateral to ends. Then because there will be like bundles of voxels, we find the representative voxel, one voxel only. Okay, leave it there. Okay, next step is among those like voxel endpoints, we are trying to find the gray matter overlap together and then try to see how many or where they are or those things. There will be this diagram. And then based on the shape and the size of the tracks, the overlap region will be different. Yeah. So example is this diagram. Okay. And the next step will be and the next step will be changing those coordinates into mask. Then you will see those green dots. Green dots. Just because I show you only the coordinate CSV file, and then if I convert it into Nifty file, then you can overlap, and then visualization will be like this. Okay, and then we might want to know where they fall into which region, right? Because if we have like all these images, okay, good, but we want to know like which voxels go into which region of the gray matter based on the gray matter standard template. And then we will find so this step 8 will be based on the step 7.
Okay. Match AAL.
Yeah. And then we are trying to find, like, based on the number 7, what will be the AAL region name. And then all this script, if you run, then you will see, again, derived, this time AAL endpoints. And then click again. Just now we saw this. Actually, the front part are the same, but at the end, you will be added all these.
So one track could have some overlap with some AAL, but some other voxels in another AAL ROI, right?
Yeah.
Yeah, so like for example, this one is the arcuate fasciculus, and it overlaps, some of its voxels overlap with SMA, some with the medial OFC, some with anterior singular.
Yeah, like
Okay.
if you want to compare like based on the C1
Yeah.
and then and the point, they will show you like or the coordinate, right?
Yeah.
And then
Yeah.
you just show like which path or like whether they have like really matched or they are not really matched but closest to voxel.
Sure.
And then if you run just that number 8 script, then you will see at the end, like for example, this voxel fall into this area.
Yeah.
And then you all have like which area they fall.
Yeah. And then you have a top
And then because
area.
it's a lot,
Yeah.
I added one more command line to see like
The top
3.
top 3.
So like top 3, top 1 is how many?
Okay.
15 voxels fall into this area.
Okay.
And how much percentage? The 85 and 58%
Yeah.
go into this area.
Yeah.
And then the other is the superior front area, and then anterior cingulate, like this. So each track, you have like all this information, top 3.
Okay.
So I think
Okay.
we can extract like meaningful information based on this because like some tracks they are might evenly distributed, or some tracks they are really focused on one region or like this, and then maybe we can later on, because we have like behavior data or like trait data, we can link to like if they are like many voxels in a certain region and then this region has like specific function, then we can make it develop based on this information.
Yeah, so this is good. I guess it's true. I mean, you have a track, and it is calculated from a template, but you know, when you project it back to each person and all that, how things goes, there may be slight differences.
Mm-hmm.
And the question or the difficulty is, how do you summarize or pick, which one you want to pick and select, and for what purpose? And it really would depend on how you want to use that information.
And I think because it's a boundary, it's a really subtle area.
Yeah.
So if you use like normalized template and then already like group template, then these slight changes make a big difference. Like
Absolutely.
Yeah, just like here, even one voxel away is not counted as overlapped. So
Right.
I think we have like good evidence to say that we are using the subject space and everything in the subject.
Yeah. And it reflects the uncertainty also when we want to extract the FA values or whatever, it is, it is like maybe this is very clearly one region, or maybe it is distributed across more regions. So the FA, when we use it, has to have some of that element as well. It's very clearly this FA, or is it more like, it's spread across different FAs. So that's, okay.
Okay, the next will be, it's just a summary. And then I found like all these information go to diverse. So I made the summary under here, where? I think, let me check again the code where I saved it. I saved the summary under under the same folder. Under the same folder, divide here, summary. So these are the summary of just now the outputs, like top 1 to 3 in a one CSV file over one person.
Oh, this is one person.
Yeah, the summary.
And the tracked.
Yeah.
And then endpoint 1. And then
two,
the top AAL.
top 1.
Second and third. Okay.
Top 2,
okay.
top 3 in
Got it.
one file.
Yes.
Yeah, it will be under the same folder.
Okay.
At the top.
Okay.
Okay. And the next color. This is the voxel count. And then from this part will be like a specific more detail of the output that we already have. So this is great to count the voxel numbers, how many voxels. Count the number of gray matter voxels per endpoint mask, which is C1 and a matched mask. And then I also made the summary.
So to link up with, say, Yancheng's stuff, the AAL ROIs here are the same as your AAL ROI labels, right?
Must be, but the one I'm using is the AL into the subject space and yours.
He also.
Yeah, then must.
I think the only difference would be if your back projection, the deformation is different from yours. Unless you're using exactly the same back projection.
He didn't use the SST, did you?
No, he used SPM's deformation, you know, the Dartel way.
I use that one as well.
Oh, then if, correct?
Yeah.
So if you are using the exact same file.
But the thing is that because Yancheng didn't do the NCKU, he only did the NTU data, NTU SCC.
Right. So, I mean, you know, if we are all dealing with the same data, it will be exactly the same.
Exactly the same.
Yeah. Okay. Right.
Yeah. And the final part will be only the scholars. Right. Okay. Yeah, final will be just extract the DTR scholar values. It's a simple. Yeah, AR summary. And then voxel count, just to give you the like how many voxels and then the matched coordinate. And then pass stats. The new tracular, good thing about the new tracular is that we don't have to do like another statistics. They will by default provide or the like frequently used the statistic values. So
meaning these?
Yeah.
Automatically.
Yeah.
For
when you
each
run
track.
the tracular, yeah, then you will.
Oh, that's nice. Okay.
That's good. Yeah.
Okay.
Yep. Yeah, and then the final will be just the visualization. Like generate matrices, then you will see. But don't much like this heat map. If you run the number 10, then it will extract, not extract, just copy and then bring the already. Let me show you. Like free surfer, if you run like here, stats. Not this one. The past label. Under here or what? I don't see here. Yeah, here under the MRI.
Yeah.
They already have like necessary FA.
That's the FAs and all that. Okay.
In the SA image, so you just again extract the non-zero value, then coordinate.
Right.
That's the script.
And then they become averaged. and then put into the heat map.
Yeah.
Okay.
And then put in here, then you can see.
So in other words, let's say if we look at one of the
Well, I think I want some modification in this script
oh,
because the heat map I don't much like.
you mean the color or what?
I tried to change the color, but more or less the same. But
Because FA values are a very narrow range. So you 0 to 1. I mean, we know FA should be 0 to 1, but in fact, most of the range is from 0.3 to 0.5.
yeah,
So you're really talking about a very narrow range, which if you use it, maybe the color will look more exciting.
yeah.
Yeah. But this is so, you
so
have...
like for the, because it's just a basic pipeline
Sure,
analysis,
sure,
I just
yeah,
put it as
I
a
know.
deferred by
Yeah.
0 to 1.
Not so important
yeah.
yet.
But if you want like visualization, I can make some modification, make it more prettier or anything.
Uh-huh. And this is, so as we expected, they are 84, right? Is it 84 or?
Let me check.
Because it's 42 tracks.
Oh, but because this is based on the AAL.
Oh, so it's 80 plus ROIs.
The 80 value based on the ROI.
Okay.
Like this.
Okay.
So when I first made the heat map, I was like, how do I understand this? So I made another CSV file like using this value. I thought it might be useful to, if you want to track like which region and then which value, how much we need. Like
but the diagonal should be 0, right?
Yeah.
Because it's the same ROI to the same ROI. So there should be nothing. Yeah, okay.
True.
Okay.
The final one. Final one will be those ranked H and then ranked ROI. So like for from the perspective of the ROI, we might want to know like for each ROI, which track force the most. Like there will be two perspectives per. First one will be like from the perspective the ROI, which track comes to this region, right? So this will be the one.
How do we read that?
So if we open the output, okay, let me.
So ROI.
Think clearly for the FA.
Yeah.
If I open.
Yeah.
For this ROI.
Yeah.
And then for this ROI, when they meet.
Yeah.
Which track?
Which track they use?
Yeah, has
to communicate.
Highest weight.
Okay,
on that point.
And the weight is the FA. The weight is the FA between these two ROIs.
Yeah.
Okay, so this is what we want. Yes.
I didn't make the visualization for this,
but eventually what we visualize would be like this.
Yeah.
So we have all the ROIs, and to every other ROI, what is the weight?
Yeah.
Yeah. Okay.
And then for this one, okay. What was that?
Rank. ROI.
This is the rank.
What does this mean?
At the point of view with the, it was ROI, for this ROI. Oh my god. Yeah, too many.
It looks like highest FA to lowest FA or something like that.
The rank ROI is my score. Yeah. made a note here. So for the ROI ranking, we just saw was that like each area region point the weighted diffusion score, right? And the final one.
So it's like the ROI that has the strongest connection to all other ROIs, based on FA or AD or whatever.
Yeah.
Is that right?
Edge. Just now I showed you was the AA pairwise connection, right?
Yeah.
Edge ranking. And the ROI ranking is...
Oh, sorry. Edge is the one. But this one, ROI ranking, is all aggregates each AALR region's total weighted diffusion score. Yeah. So for this ROI, what is the diffusion it has with every other all the ROIs combined?
I got it. Yeah. You got it correct. Yeah. For each ROI.
Yeah.
For the rest of the ROIs.
Yeah.
Or the edge means like between two ROIs.
Between two ROIs.
Yeah.
Yes. Okay. I think for us more informative is the edge ranking, right? Yeah. But the ROI ranking is also important because it might be that it is basically a very connected one versus it's not. Okay.
Yeah.
All right. Yes.
Okay. Yeah, this will be just directory tree and the output files that we have at the end. So for example, yes, correct. Yes, for the data subject, and then there will be like GM and a WM, but for today it's WM. And then it started from free surfer, and then if you run the recon or then you have scripts that surface touch trash, and then Tracula will have prefix with D, and then important is D pass. It must have like 42 folders. And then each folder inside you have the endpoint information and the images.
Your screen, that one is not showing it.
Oh my god, sorry. Maybe I already
Oh, yeah, it's because you have two screens and then...
Yeah, and I think I have to close the...
Yeah, quit the PowerPoint.
Yeah.
Yes. Okay.
Yeah. Once you run the Tracula, you have the prefix D folders. And then this FS average, I didn't do it when you run the recon or any Tracula, you automatically link to here, so you just can't ignore it. And then derived will be mainly about the endpoint information. And then overlap the region with the C1. And then AAL information, RI information. And then for the region, you have the heat map and the rank edge, rank ROI. Rank ROI is for like each one RI region to the rest of the RI regions. Edge will be like in between the ROI regions when they meet. And then under Tracula, you have the DM, RI, RC. You just can't ignore it. Yeah. Like this, basically. Okay. And if you want to check whether you did it correct or not, for the code, I added the readme here. You can check this one. This is the tree. Like after you run all the analysis pipeline, then you have to have like this kind of format, like just I explained.
Right.
Including gray matter.
Very nice.
Yeah, more or less. And then if you read this README, like for 2 days presentation, like by step, have a clear and detailed information, explanation, what to run and how to run, like step by step, all these things. And input and output.
Okay.
Okay.
Very cool.
And this is the template.
Yeah.
Why didn't make more detailed explanation on this template? Because template this every time will be different.
This one you did it from Chunwei's, yeah, so she did the Dartel already and did that. That's why you have this deformation.
Yeah.
So that's why if you are doing on the same subject, actually it will be exactly the same.
Yeah.
Right. Mm-hmm. Yeah. Which goes to the next thing to mention, or the last thing to mention, is that so for Yancheng you have voxel to voxel distances, and each voxel can be categorized into different AAL ROIs, correct? Okay. Then you have the ROI to ROI edges, which can have different FA or MD or whatever value, okay? But you have the ROI to ROI edges, and each ROI includes all those voxels that Yancheng deals with at the geodesic level, right? So that when we plot the heat map, I think we did this somewhere along before. You can have a cluster of voxels that are part of like one ROI, right? Then that has an edge with another cluster of voxels, which is another ROI.
Something like in the end, we will have like this kind of diagram, but in a like grid.
Yeah, those things. And then all of these voxels, FA, all of this edge FA is that FA value which is the edge rank or rank edge thing, right? Yeah, so we just take that and put it into the matrix, right? That would be theoretically correct. And then we can compare those FA with the geodesic distances, right? And functional, and similarly functional connectivity values, right? So then that would be integrating the gray, the white, and the functional data all in one connectome, theoretically, for one subject.
Yeah.
Okay.
Yeah, and then another idea is that if we want to add like behavior or like characteristic or whatever the data, then we can add, and then we can see like for this kind of person like who has like high anxiety.
Yes, what are the
then
behavioral?
we can look into the boundary, and then we can see like how they differ between subjects.
Yes.
We can try to find
while we are getting
which region in theory are like.
So we are getting very, very close now, so to BrainWorld. So we need the final, so all these different parts are now more or less okay, and the next thing would be the integration of these, right? Into into a whole, plus mapping it to the behavior measures that we have, which is kind of the behavioral tome or whatever, the behavioral connector. Cognition, mental health, resilience, psychiatric, and demographics, right? And how that, and Junwei has that, which is we should do canonical correlation, which is that you can do a canonical correlation between the behavior and the multimodal connectome, brain connectome, and then see how the different profiles are associated. Yeah.
So I'm currently running under NCKU data, which has like about 330.
Yes. That's Junwei, the same thing as Junwei is doing?
Same
okay, good.
Data
Okay.
list, and I'm running Reconor and Trochler almost 70% done.
Oh,
Yeah.
okay,
Because it's
almost
still-
there.
Because I've been running the loop over a few weeks now, and then at the same time, I was like, I couldn't wait, and I opened another window and
I should
run
do
the
it again.
parallel segmentation and all these things.
Yeah, you
are
can do
done.
things in
Yeah.
parallel. it
Because
will-
at the end, like the Python script are really
it's
quite
the same.
quick.
Yeah. Does this include the functional connectivities? Does your pipeline include the functional connectivities
Yeah,
of
I'm
these
also
subjects?
running
Oh,
yours.
okay. So you're running all of these on the NCKU, including the geodesic
Yeah,
and the
yeah,
thing.
but I need your help that you need to make develop the version with the directory at the top, because like his script, like you need to type like the directory and
Or
each
in
cell.
each,
Yeah, so I want,
move
I
it
want
all
it,
to the
I
top.
want it, yeah, I want it like develop the version as just can just run the loop, just run the loop.
Well,
Because I can ask like Gemini to edit it or
But you're
anything,
not
but you need to revise,
Yeah,
but not
yeah.
really specialized in. So I need your confirm, like to whether
Yes,
they
yes.
did okay everything.
yes, in all of these, we can have the AI help, but at the end, you still need to, you're not confident. So
yeah,
you still need.
I think Yancheng, please just put like your script into Gemini and then call Gemini to update. Yeah, because I did the same for my script. When I finalized the script, I just ask Gemini to put everything in a like same format.
Yeah.
Put everything like loop at the top, directory at the top, and I
it-
run again. Like
and it's
I
okay.
told you before that I'm just using
yeah,
this
yeah.
script as a like beginner, and I run it. Of course, you have error. Then you need to fix it, and then you will have the finalized version.
Yeah. But still, it's faster. It's faster than if we do everything ourselves. So, but just have to be careful to check. Yeah. Very, very cool. All right. So we're getting there, and you'll just keep running it. So you're saying run 70%, but his data also takes out a lot of space, right?
But I'm running on 50, server 50.
So how much space so far?
When I checked a few days ago, it was quite plenty.
Okay.
Yeah. Okay.
All right. Well, just make sure we're not hitting some high end of the hard disk space. If we need to, we actually have a lot of space now. It's just now William is moving things around. There is some crunch, but once he's finished, actually we have quite a lot of space.
When I uploaded the data last night, I checked like this person take up like 2 gigabytes.
Really?
Yeah.
That's very small.
Yeah.
Including the functional connectivity
No,
and everything.
no, only the Y matter.
Oh, but what about the? I think the
A
other.
lot.
If you add that together,
Like more than
no, one person how much space?
20, wasn't it?
Gigabyte.
Wasn't it 20 over?
Less than 5 gig. Delete the Also, after you clean up, the essentials are about 5 gig. 5 gigabyte. Then you say yours is about 2.
Yeah,
So
because
each person is about 7 to 8, 10
yeah.
gig. Right.
Because yesterday when I tried to upload the data, I just copy and paste the whole subject, whole data including gray matter, and I found it too big, so I just removed the gray matter, only downloaded the white matter. And it was 2 gigabyte.
Rough calculation, let's say each person is 10 gig. Totally you have 300 people, right? You said?
Yeah.
So 10, 300, 3,000 gig isn't that 3 terabytes?
I'm not sure.
Is 3,000 gig 3 terabytes? Well, that's very small. I'm surprised. Okay, well.
Yeah, a subject was 300.
Well, it's the memory. The memory is the issue. Yeah, these data are low-res data for fMRI because they are the 3 resolution, not the multi-band one. So the multi-band one will be crazy. Yeah, the multi-band one will be crazy.
Yeah.
But here, okay. All right. So
1.5.
So I'm not too worried. I think it's manageable. So it's just time. We just let time continue, and then we can have something very interesting to look at very soon. Okay.
Thank you.
All right. Thank you. And any questions? Or anything to add? No? Yeah?
Just I want to clarify that. So for each track, there's a voxel cloud for each end point, right? And then you calculate, I would say estimate the matching gray matter voxels to each endpoint's voxel cloud.
Yeah.
Is that right?
Yeah.
Okay, so first I want to ask is that how do you define the cloud? What's the threshold of the probability? Do you setting any threshold?
Oh, actually, the tracker already provide. They already decide this is the endpoint. This is the endpoint too. But I need to check like how much threshold they decide to. They use to decide these are the endpoints. But that is not something I calculated or something.
Oh, okay.
It's already preset in the tracker.
Okay. So
I will check later and then send you DM.
I see. And the next point is that is you did tolerance test for to define which if it's matched to the gray matter voxel. So and you say that
at least
you
one.
said less than one voxel size, right? So the voxel size is the T1 voxel size, or
let me check. I get your point. I need to check the code. That was this one, right? C1, yeah. Oh, C1 is from segmentation. No. Yeah, I did it myself using Yan Cheng's template. Like for the gray matter order, yeah.
Resolution.
Yeah.
Okay, okay.
So is that good? Is that better? The T1 resolution will be higher than the
Yeah.
fusion resolution. So it's stricter. It's a smaller range. Because if you use a poorer resolution, it means it's a thinner range.
Yeah.
So you'll actually be more strict.
Okay.
All right, so thanks, Wooyoung. It's excellent. And for those of you who are watching this post-recording, I posted, and those in our lab, we have our lab workshop, but this is also simultaneously in BrainHack School. You have the GitHub, which Wooyoung has posted, right? And I copied the GitHub link onto the Discord as well. You see, oh, actually, no, Wooyoung, you're not sharing on the Google Meet. The screen is not on the Google Meet.
Is it? No?
Yeah. No, now it's the PowerPoint. The Google Meet has this PowerPoint
You
slide.
want to share the Discord?
Yeah, you can share the Discord
Okay.
screen. But just to show everyone, yep, there you go. So the link to the GitHub is above, higher. There you go. Okay. So the GitHub is where these tools are also, if people are interested, you can use them. And if any questions, of course, you can pose and ask us. Okay. I think that's it for today, and that wraps it up for some of our labs' recent methodologies that we are working on. And then I think from here on we don't have any more presentations or workshops in the near future for now, but I think this is already a lot. So yeah, we just continue, at least for our lab, we just continue to use this and then apply on those 300 people's worth of data, and we see what we get. Yeah. All right, thanks everyone, and we'll call it a day. Bye.
No, okay. No. 50 I all have because I mainly run on